Hi folks, and welcome back to Physics with Captain Rod. Purpose of this video is to demonstrate how to use graphical techniques to analyze the motion of a system. And the system we're going to analyze right here, we got Donald Trump's new rocket here. He bought up some rocket company and they've developed their little spaceship here. And this is right before the election. Donald probably put Hillary Clinton on the rocket and he's going to try to shoot her into orbit before November. It's probably his only chance to win. So we're going to assume that this rocket here has an acceleration of about 15 meters per second squared. And in my current class here, I haven't talked about gravitational acceleration yet, but that's about 1.5 times the acceleration of gravity. It's a pretty stout acceleration. And what we're going to do here is we are going to try to calculate the time it takes, how long for that rocket to reach a height of 300 meters, starting from rest and accelerating at 15 meters per second. So, first thing we always want to do in these problems is a coordinate system, because position, velocity, acceleration, these are all examples of vector quantities. And the plus and minus signs on vectors don't even make sense until we attach a coordinate system. So I'm going to go ahead and put a coordinate system in this problem. It doesn't really matter where we put the coordinate system. I'll go ahead and just put it at the starting point of the rocket here. X, Y. And I'm just going to use a good old-fashioned standard right positive coordinate system. X, Y. I'm going to go ahead and draw a motion diagram for the rocket. So just using this dot here to represent the rocket. And then as time goes on, the rocket's moving faster and faster and faster. So these dots would be further and further apart. Okay. I'm going to go ahead and sketch the velocity graph for the rocket. And that's where I usually recommend people try to start with these. See if you can draw or sketch the velocity curve for the particle you're dealing with. So, velocity against time, taking note that at t equals 0, the rocket isn't moving yet. So graphically, that would put a point right here. Now, we know that the speed is going to increase, and we're going to assume that this acceleration stays constant, which would give us a linear velocity curve. So this curve might look something like this. Doesn't really matter when you're just sketching the graph whether you draw it like this or like this or like this. It's your picture. You're free to set a vertical scale. Now, what I'm going to do here, though, is I don't know the time. I'm just going to call that time t. We don't know a numerical value. And we don't know this yet either. But this is described by some function that for a moment I'm going to call v of t. There's a couple ways to get this function. I'm going to get it like this. Since I know something about the acceleration, I know that acceleration's equal to change in v over change in t. In this example, I know the acceleration to be 15 meters per second squared. I'm going to put NCU here, which stands for note consistent units, equals, all right, now, this change in V can be written V final minus V initial, but this rocket started at 0. Since the initial velocity is 0, I don't really need a final on here. I could just call that V. And then the delta T is going to be T final minus T initial, and I'm going to start timing that rocket at T equals 0. And if we solve this equation for V, we get 15T. Now, we can go through this little exercise to find that function. In physics class, a lot I usually just, I look at alternative approaches. We could also say, okay, this thing is a linear function. We know that the acceleration is the slope of that line, therefore the 15T. And then the intercept is 0 basically by observation. And I would take that most of the time to come up with that function. All right, now we're going to go to the position function. I'm going to draw this up here because I always draw position functions above the velocity functions. Now, in this example, it isn't x that's changing, it's y. It's the y coordinate of that rocket that's getting bigger and bigger and bigger. It's at t equals 0, the rocket's starting at y equals 0. Now, if the velocity were constant, we would have like a linear curve here. but it's not. We're going to get some sort of curve that's concave up. So I'm going to go ahead and sketch that, maybe something like this. Right, and this would be concave up because the speed of the rocket's increasing. Right, therefore, the slope of the tangent line has to be increasing. Now, as far as coming up with this equation here, so I'm going to come right up here to the same point above it. And then to get that equation, I'm going to just take note of the displacement of the rocket, delta y, is given by the area under the curve, under the velocity curve. So if you're not familiar with that, go back and you can look at my video on how to find the displacement for a particle from a velocity curve. This bound area right here is going to give the change in position for the rocket. Now this is a triangular area, so 1/2, the base is t, and the height is 15t. And this ends up being 7.5 t squared. Now this is equal to delta y, which is y final minus y initial, but looking at my graph, y initial is 0. So I'm going to go ahead and just label this function here. The equation for y is going to be 7.5 t squared. So what we've done now is we've put in a coordinate system and then drawn velocity and position graphs with respect to this coordinate system. Starting with the velocity graph, come up with the equation for the line for the velocity function here based on the acceleration. Then we use the area under the curve here to come up with the equation for the position function for the rocket. All right, so now what I'm going to do is actually try to find that time. So what we're actually looking for is the time for the rocket to get 300 meters. And this function tells us the y coordinate against time. Whoops, and I think I accidentally erased that square there, but 7.5 t squared right from here. So I'm going to go ahead and just write this over here, 100, and again, note consistent units. All units are consistent. I'm sorry though, not 100, 300. 300 meters equals 7.5 t squared. And now what we need to do is divide both sides by 7.5. Would somebody give me a value for that, please? What's 300 over 7.5? 40? So this is going to read 40 equals t squared. And then we would square root both sides. So t is going to equal, somebody give me the square root of 40? Say what? 6.32. Let's just say approximately 6.3 seconds is good enough. If we want to know how fast the rocket's going, we could take that 6.3 seconds and sub it into our velocity function, but I'm going to save that for another time. So again, the point of this video is how to use a velocity graph to write a position function for a particle, and then use it to solve a basic problem in physics. In this case, we've got the time for Donald's rocket here to get 300 meters high. Hope this video helps everyone understand these concepts. Have a great day.